object-based image analysis for Earth observation data under the webinar series. Before starting the session, I would like to pray to God for the well-being of all my colleagues who are undergoing severe COVID infection, and also pray for the entire mankind to be safe from this COVID. To start with heavy heart, object-based image analysis for Earth observation data. I'm Minakshi Kumar, a scientist at Photogrammetry and Remote Sensing Department, Geospatial Technology and Outreach Program Group at Indian Institute of Remote Sensing, which is a part of Indian Space Research Organization. The prerequisite to this session is that I hope that you all have a basic knowledge of remote sensing, the basic concepts, and you are familiar with various concepts of resolutions. Then once you know remote sensing basics and you are familiar with remote sensing images, then you can interpret those images either using the visual interpretation method or doing the digital image processing concepts, right? Especially the concepts of image classification, methods of supervised and unsupervised classification. In addition, a knowledge of basic image statistics would also be very good for this session. So the session would like to discuss here the traditional image analysis approaches and what are their limitations. Then the object-based image analysis concepts, the image segmentation methods, and some case study examples. So I will start with the traditional image analysis. So you know remote sensing images captured from satellites, sensors on board satellites orbiting the Earth. They are capturing data in multispectral framework, you can say. Many different spectral bands are captured for the same area. So there are two methods of interpretation: the visual image interpretation and digital image analysis. The visual image interpretation is act of examining those images to identify the different objects and judging their significance. For visual image interpretation, we use a number of elements of image interpretation, like, for example, shape, size, tone, texture, pattern, height, shadow, association, etc. to identify different objects, like, for example, here the bigger aircrafts, the smaller aircrafts, the oil storage tanks, and a number of tanks make it a oil storage depot, maybe. The mountainous roads versus the highway roads with flyovers and all. So we are interpreting these elements, these objects, using different elements of interpretation. So when we are doing visual image interpretation, we are not seeing the pixels. We are not classifying the pixels. In fact, we are trying to identify the homogeneous objects as a whole, evaluate their characteristics, and judge their significance. So maybe this is a house. A particular vehicle on the road is a car or a bus, depending on the shape, size, etc. So we are identifying the objects, evaluating their characteristics, and judging their significance. We are not, in the satellite images also, we are trying to identify which one is vegetation or urban area or grass or water body, etc. So we are not classifying the pixels in the visual interpretation. But in digital image processing, we do precisely that. We use pixel-based classification methods of supervised classification or unsupervised classification to label each pixel in the remotely sensed image with one of the labels, either as a spectral class or as a land use class, depending upon the method of interpretation. Now, the limitation here in digital image analysis is that we are doing the classification based on a single parameter. We are doing it based on a single parameter, which is the spectral information alone. In visual image interpretation, we are using the guiding properties or different elements of interpretation. In digital image analysis, we are using only one of them, that is tone. Now, the problem here comes is that when I'm trying to label one pixel to a class, the one pixel may be similar to many classes. So that results, as you can see here, in the salt and pepper effect, because the pixel-based classifiers, they ignore the spatial autocorrelation, how the neighboring pixels are associated with the same class. So the spatial autocorrelation is normally ignored in the digital image analysis. So one more thing which happens here is, as the resolution of the imagery goes on increasing, the information content goes on increasing, but the accuracy of the classification goes on reducing, it decreases. This could be due to the within class variability in the high resolution images. So to overcome this drawback, the pixel-based classifiers were modified, and there was a series of advanced classifiers which were available, like for example the artificial neural networks, which could integrate the additional data, maybe one more layer of an elevation or a land use or any other information, which could be incorporated along with the spectral value. So that was one. Then there were texture-based classifiers, the soft classifiers based on fuzzy logic, support vector machines which are classifying based on determining the optimal hyperplanes, the expert classifiers, the decision-making rule-based classifiers, all for increasing the accuracy of the pixel-based classifier. Whenever the resolution goes on increasing, the class variability increases and the classification accuracy was decreasing. So to overcome this, advanced classifiers were used. But still, only one or two of the guiding force parameters from cognitive analysis from visual image interpretation were used, like for example textures or elevation, right, or a land use map, which could be integrated with these type of classifiers, but not all the visual interpretation elements. So it formed the basis for object-based image analysis, OBIA, or basically geographic object-based image analysis, GOBI, for our Earth observation data. Now, the main concept of object-based image analysis is that the basic image processing units are image objects and not single pixels. So basic image processing units are image objects and not single pixel. What is image object and segment? We will discuss further. So this object image analysis was developed because it supports the cognitive analysis which we use in visual interpretation. That means in visual interpretation, we were able to use the shape, size, tone, texture, pattern, etc., the different elements of interpretation. So that cognitive analysis we can incorporate in the object-based analysis. So basically, object-based analysis is a knowledge-driven analysis which uses spatial autocorrelation. Right? This spatial autocorrelation, as I told in the limitation of pixel-based classifiers, pixel-based classifiers were not using the spatial autocorrelation. Here, they are growing into homogeneous regions, and so the spatial autocorrelation was considered. Right? So it not only uses the pixel values, but also the spatial values to characterize the shape of the region. Then the classification process becomes fast because you are classifying the objects and not single pixels. So mainly it was developed for high resolution images, but what we realized is that it also works very good for medium to low resolution images. So object-based image analysis becomes the technique to classify the remote sensing images. Right? So the object-based image analysis, the basic image, the units are image objects or image segments, right? So this object-based image analysis divides the entire image into regions. And this region categorization is based on the spectral values as well as some shape or dissimilarity values, right? So converting the image from individual pixels to a image object level or a group of pixels. So next we should see the what is the image objects. So image objects basically are a group of pixels having common properties, having some common property. This common property could be color, like for example here, all pixels belonging to this in this part are same color, all pixels in this part are same color. So the object or segments are a group of pixels having some similar property, like example is the color or the shape or the area or a scale or any property. Even if it's a video image, even the motion could be one of the property to group pixels. Okay. So that is an image object. So since in object-based image analysis, we will be working on image objects or segments and not single pixels. So we should first study the techniques for segmenting an image. To convert an image from pixel to objects, I should first study those techniques. Okay. So we should study image segmentation. Then image segmentation can then be defined as process of dividing an image into regions of related content. The process of dividing an image into regions of related content. We can say, in other words, that it is process of subdividing or partitioning an image into homogeneous regions. Like for example, all these pixels are similar, so they belong as one region. So partitioning an image into homogeneous regions and non-overlapping. The homogeneous regions should not overlap. It is not that if I have one segment, this can be another segment. No, overlapping is not allowed. So this is image segmentation, process of dividing or partitioning an image into homogeneous and disjoint regions of different statistical behavior called as image segments. This is image segmentation. So then what, if this is segmentation, then what are the various segmentation algorithms? In the previous slide, we defined image segmentation as process of partitioning an image into homogeneous regions of related content. Homogeneous, non-overlapping, like these are non-overlapping. So homogeneous regions of non-overlapping regions of related content. So that means my segmentation algorithm also are based on these two properties. Homogeneous means similarity and non-overlapping means discontinuity. The two regions should be non-overlapping, they should be discontinuous. And the homogeneous regions mean the region should be, the pixels belonging to the same region should be similar. So the first category, that means discontinuity, is to partition an image based on the abrupt changes in intensity, for example here. And the second category, which is similarity, is partitioning an image into regions according to a predefined criteria of homogeneity, similarity. So once we do segmentation like here, here or here, the pixels in the same category, they have similar values. That means they are similar. Either their DN values are similar, that means tone is similar, or texture is similar, right? And pixels in this category, they form a connected region. So this is a connected region. This is a connected region. And neighboring pixels, the neighboring pixels that are in different categories have a different value, different dissimilar value. So this is what is meant by a successful segmentation. So now we will see different methods of segmentation. So segmentation then methods will be based on two algorithms: region based, that means similarity based, or the dissimilarity, discontinuity based, basically the boundary based methods. So there are a number of region based segmentation algorithms, and similarly a number of boundary based image segmentation algorithms. The region segmentation algorithms are thresholding, clustering, split and merge, region growing, and multi-resolution segmentation or object-oriented segmentation. Whereas the boundary-based segmentation methods are based on the boundaries, based on detecting the edges between different categories. And they are basically the convolution filter-based and watershed segmentation is a part of boundary-based segmentation. So now we will see them one by one. We'll start with the region segmentation methods of thresholding. Now, thresholding methods are basically histogram-based. They are histogram-based methods. All of you are familiar with the histogram. The histogram is a graph of data distribution. On one axis, we have the dependent variable. In our case, it is the DN values, the brightness values, intensity values in an image. And on the y-axis, we have its population, the frequency. So this is I'll come directly to the image, to the histogram. So this is an image of a fingerprint with the light background. Okay. But as you can see that the light background is not very light, it is grayish, and the finger rings are black. So if I plot the histogram of the fingerprint image, the background white is also varying from 127 to 255, and the black finger rings are also from 0 to 127. Now, if I have to match this with an access controlled system database or a client controlled database, right? My finger rings have to be very precise. The image should be either it should be a bitmap, either the finger rings or the back. Right? Only then it will match with the database. So that means it's very essential for that once I'm coming and swiping my finger, a biometric access, to match it with the database, it should be segmented into two categories, finger rings and non-finger rings, so that it will match with one of the data. So we have to segment this image. Now this is very easy, as we can see that this is a bimodal histogram, one peak of white background, one peak of black finger rings. So, and there is a dip in between. So I can take a threshold at 127 here, and all values from 0 to 127 can be segmented as black finger rings, all values from 127 to 255 as white background. So that means I'm identifying a threshold T here, and all objects, all data points below it are my object points, all data points above it are my background. Right. Similarly, I have another image of a black cloth now, total reverse of the first image, black background and a white object. Right. But here now the two peaks are not very well defined. That means the white rice peak is not very well defined. So how to choose a threshold? I could have chosen the threshold here or the here. So if I change my threshold, then the optimal, my size of the rice granule will vary. And we will not be able to judge the quality of the rice. So then the image processing methods are automatic in nature. So we start with an initial estimate of the threshold as T here, and all objects from 0 to that, this first threshold, estimated threshold, becomes my, and I will cluster this image into two, black and white. All data points from here to 0 to this value, threshold T, which I've estimated, will be black, and all values from here. So if I take my first threshold here, so all this will be black region, and all this will be white. Right? So then what I do is, I do it iteratively. I take the black region and find its mean. I take the white region and find its mean. And I compute a new threshold, which will be half of the black and the white region. So now the threshold will change. Threshold will change from here to here. So if this was threshold 1, this becomes threshold this in the second iteration. Again, segmentation will be done. This will be black and this will be white. Right? Again, a new threshold will be computed till the threshold converges. Right? So then the optimum threshold will be computed, and we will get the optimum size of the rice. So this is histogram based thresholding, but again the limitation here is it is using only one of the parameter, that is DN value only. It is not taking the spatial autocorrelation. So this is also one of the crude method of segmentation, the single parameter based segmentation. Now, the previous examples which I showed you were bimodal, right? Only two peaks, very easy to identify the thresholds. Remote sensing data is not so simple. Remote sensing data is multispectral in nature. That means it has being multispectral in nature and many land uses, it has number of peaks. It has number of peaks. For example, this actual histogram is for this image of Lena, but the remote sensing histogram is similar in nature. That means it has a large number of peaks corresponding to the number of classes in the scene. But the concept is here again same, that there are threshold the dips. There are dips which are separating the peaks. So it is to identify the multiple thresholds and segment it. Like for example, if this is threshold 1, so 0 to this threshold 1 will be region 1. Threshold 1 to threshold 2 will be region 2. Threshold 2 to threshold 3 will be region 3, and so on. So multi-modal data like remote sensing data can also be segmented using multiple thresholds, not a single threshold. So this was the example on Lena. You can see that the outline of the hat, face, shadow still is preserved even after we have done the segmentation. So same thing happens in the satellite images or a very high resolution UAV images. UAV is unmanned aerial vehicles, so drone images. So this image also has, like for example, here this is the histogram of this image, one of the bands of this image. Right. So if I apply multiple thresholds, we can still segment different type of trees, roads, road markings, even vehicle. So all get segmented. Even you can see the cars are also properly getting segmented. Not only cars, their shadows are also well separated using the even the thresholding techniques. Okay, so the first method was thresholding. The second method is clustering. So clustering is finding the natural groupings in the data. Finding the natural groupings in the data. So it can be well explained using the graph of data distribution or a scatter plot. So this example I have taken is that suppose there are 9 pixels in the image, 9 or 10 pixels here, and I have to categorize them, or I have to cluster them into 2 clusters. Then we can start with an initial random estimate, right, of 2 clusters. So one cluster could be here, the other cluster starting beginning could be here. And then distance of each pixel to each of this cluster is computed. And the pixel will be labeled to that class or to that cluster wherever the distance is the smallest. Like for example, this pixel will go to this cluster, this pixel will go to this cluster. So I get 2 clusters because I started with 2 clusters. Now it should not end here because my starting point was random. So after the first iteration, all the pixels which are going to cluster 1 and all the pixels which are going to cluster 2, a new mean is computed. So mean position shifts now from here to here. You can see the mean is shifted from here to here. So again, all pixels will be reclustered, will be reassigned to different clusters. And you can see that initial this pixel was in cluster 1. Now it moves to cluster 2. This pixel was in cluster 1. Now it moves to cluster 2. Okay. So this will shift. The pixels will keep shifting from one cluster to another till they converge. That means number of pixels do not shift from one cluster to another, right? Or a number of loops have been done. So this clustering method is called as either k nearest neighbors or k means, or even migrating means, because means keeps on shifting, or mean shift. So different clustering methods are based on the same concept, finding distance between the pixel and our initial estimate, and then group finding the natural groupings. Like for example, that same very high resolution UAV image, I tried to find out using k means the 6 clusters and the 12 clusters. So even the clustering is able to separate out my major classes. But if you see, if I take only 6 clusters, my the cars are coming as a whole. Whereas in the previous one, I could separate out the windshield as well as the shadows of the cars. So this is my clustering based segmentation algorithm. Then the third one, which is very popular, are region based segmentations. 2 general approaches, a top down approach and a bottom up approach. The region growing is a bottom up approach and the region splitting is a top down. So region growing approach, it starts with the manual seed point and it grows the region. It grows the region until the entire image is segmented. So region growing techniques, they start with 1 pixel of a potential region. For example, it may be here, and they will add the adjacent pixels to this region till the region becomes very distant. Right? So the first pixel, how to start a region, it could be random seed points, a number of random seed points, or the first pixel could be taken as a first unlabeled pixel to start the region growing method. And a statistical test like either standard deviation or variance, the mean can be used to decide if the pixel can be added to this region or not. So that is the region growing technique. Like for example, I have taken a random seed point here and it grew my road marking into it grew the road into one class as a region, separating out the road markings and you can see the what is called the divide. So this is first method, which is region growing. The region splitting is the opposite of region growing method. Region growing method is a bottom up approach, starting with 1 pixel, and region splitting, it starts with the whole image. It will divide the image into sub images or equal parts, and until the homogeneous segments. And there is a combination of split and merge algorithm. That means after every splitting, the adjacent segment should be combined. So this is that method, region splitting as well as region split and merge method. So here it is a top-down approach. It will start with the assumption that this entire image is homogeneous. If not true, the image will be split into 4 sub-images. We'll start with the assumption that the entire image is homogeneous. If not true, then it will split the image into 4 sub-images. And it will check for homogeneity of each sub-image. If the sub-image is homogeneous, it will not split it. But if the sub-image is not homogeneous, it will again split it into 4 sub-images. And then the splitting can continue till we reach either a pixel level, that means no further subdivision, or the homogeneous regions are achieved, like here. Right? So this is the region splitting method. Now there is a split and merge method, because when we are splitting, it will create regions which are adjacent. Like for example, these 3 regions which are adjacent and homogeneous, but there is a boundary between them. You can see this image, it's homogeneous here, but I can see the partition. So split and merge method is an iterative method. That means after each splitting, it will check for the homogeneity of the image. It will you can say merge the regions which are similar. Like for example, here now you can see. So it has merged these regions which were similar. So the split and merge method will produce more compact regions. You can see another example here. So this is here, you can see the partition lines are splitting. Here they are grouped together, so more smoother image in the split and merge method. Then comes is the multi-resolution segmentation method, or object-oriented segmentation. So this multi-resolution image segmentation method is a region growing technique only. It's a region growing and region merging. Region growing, region merging technique, which starts with 1 pixel object. Right? So here, like for example, the raw image, which is pixel level, each pixel is assumed to be a region. Each pixel is assumed to be a region. And in the next step, the pixels will be grouped together. Now, since we are assuming each pixel to be a region or an object, so in subsequent step, smaller objects will be merged into bigger ones. Like for example, these pixels are grouped together and formed as this region 1 or image object 1. So these pixels are grouped together here, and this is region 2. Then in the next level, in the next subsequent step, these smaller objects will be grouped into bigger ones. Like this, and this one was grouped into the bigger. And more objects were grouped into the more bigger objects. So this is a bottom-up region merging technique, starting with 1 pixel, and in subsequent steps, these smaller objects are merged into the bigger objects. Now, what is the criteria for merging? The criteria for merging is based on a local homogeneity criteria, right, that describes similarity between image objects. That means if this and this is a adjacent image object, so a local homogeneity between these 2 regions will be checked, and they will be merged together. If they fulfill the homogeneity criteria. And how long this merging should continue, that is determined by a scale parameter. So if the smallest growth exceeds the threshold which was defined by the scale parameter, the region merging will stop. So throughout the segmentation procedure, whole image is segmented into image objects based on several adjustable criteria of homogeneity, which is defined by color and shape. What it is, we will discuss in the subsequent slide. Right, so several adjustable criteria of homogeneity in color and shape. Right. So there are two things. One criteria is color and shape, one is scale. Smallest growth exceeds the threshold defined by scale, the process will stop. So the scale parameter, basically, it is an abstract value which determines what is the maximum possible change in heterogeneity. So in other words, it's indirectly related to the size of the image segments that are computed. Like for example, you can see here in this example, when I have a scale parameter 25, I have smaller objects. When I have scale parameter 50, when I have a scale parameter 50, the number of objects are bigger. The number of objects are smallest and the size of objects are bigger. Like for example, you can see this particular object. It's formed by grouping of all these objects, right? They are grouped together to form this object. Then similarly, this one is a combination of these objects. And when the scale parameter is 100, the number of objects are even less, but the size of objects are very small. Yeah? Like you can see, this one is combination of this plus this plus this. So all these objects are combined together to form this image object. So this is the scale parameter. So scale parameter is related to the size of the object that is created. So heterogeneity at a scale parameter is directly or linearly dependent on the object's size. Homogeneous areas will result in larger objects. Heterogeneous areas will result in smaller objects. You can see that here. Even when we are changing the scale parameter from 25 to 50 to 100, this is a homogeneous object, so it gets grouped. But the small trees and shadows are still separable from here to here. Right? So they are separate. So small scale parameter will result in the smaller objects. Large scale parameter results in the larger objects. So this is multi-resolution image segmentation. Multi-resolution image segmentation. So the first criteria was scale parameter. The next criteria is the color and shape. So color is actually the pixel value, the DN value, and shape includes the compactness and smoothness of the geometric features. Right? So color and shape are actually complementary to each other. They are complementary to each other. So if you are using a particular value of shape, like for example 0.3, then 1 minus 0.3, 0.7 will be your color. So this is done when you have the color which is prominent. If your shape is prominent, if you have a very, very high resolution image, you can increase the shape value. Then next thing is to be considered is the neighborhood. Whether we are considering the immediate 4 neighbors or all the 8 neighbors. So if I'm taking only the 4 neighbors, right, I will have smaller objects. If I take 8 neighborhood, then my the objects would also be bigger. Okay. So that is what I explained here, the 4 neighborhood connectivity and 8 all diagonal connectivity. So now once we have segmented, the next step is classification. Now classification here can be done using the simple nearest neighbor sample based classification or even the rule based soft classifiers, fuzzy classifiers. Right? So and now in the standard nearest base neighbor classification based on samples also, we can not only use the simple layer values, but we can also use the shape size, the geometrical properties, or the textile properties, or the hierarchical properties. That means all the cognitive analysis which we use in the visual image interpretation can be incorporated in the object-based classification, either sample-based or rule-based. Right? So we can have relationship to the senior objects or the neighboring objects and so on. So many features are available for classification other than what was available in the visual image interpretation. And you can see that the classification results are so very smooth. The classification results are so very smooth as compared to the pixel based classifier, which I will show you in subsequent slide. Right. So as I said, we can do sample based classification, and sample based classification is similar to your the pixel based classifier algorithms. That means you are marking a training sample, and now instead of all pixels, we have now regions. So regions will be classified to those samples, right? Or you can define the fuzzy rules, hierarchical rules, knowledge-based rules for classification. So this is that example which I told you. I'm using here LIS4, that means linear imaging self-scanning LIS4 sensor onboard Indian remote sensing satellite series. The same image is classified using maximum likelihood classifier, which is basically a pixel-based classifier, and an object-based classifier to classify into same classes. And you can see the classification results are so smooth and accurate, where here it is appearing the speckle-based. So OBIA classifier is even better than the pixel-based expert classifier. Expert classifiers you can see as compared to the expert and MLC, here both are pixel based. So expert is having much more accuracy than the pixel based, and the OBI is even having much higher accuracy. So this was LIS4 data, which is 5.8 meter resolution, and the UAV data which I showed you in the earlier slide, which is 3 centimeter data, which I forgot to point out. So the maximum likelihood pixel based classifier and object based nearest neighbor classifier, the results of the object based classification. Now, so these were the boundary based, these were the region based methods, and I told you that the segmentation algorithms are based on two properties. One is similarity, and one is the boundary based, the detecting the boundaries or the edges. So the boundary based methods are primarily based on the use of the convolution mask. And convolution, if you are familiar with digital image processing, it's process of evaluating the weighted neighboring pixels around a central location in the image. For example, and it takes convolution mask. For example, here is window mask with some constants. It is placed over the part of the image. So this is the central location, IJ location, and it is being evaluated based on its neighboring pixels, right? So this central pixel value, a new value is computed by multiplying and adding the constant with the brightness value, adding them all together, dividing by the sum of the constants, and the central pixel value is replaced by the new value. And then this window is shifted by 1 pixel to the right. This becomes the new pixel value, new pixel under consideration. So it will be undergoing the same formula and will be replaced here till the entire image can be computed. So this is convolution technique, and based on this convolution technique, we are basically extracting the edges, right? High pass filtering, extracting the edges, convolution based filters. So Sobel filter, Prewitt filter, Robert, Kirsch, Laplace, etc. So on the satellite image, you can see the output of Sobel filter, making the boundaries segments around the boundaries. And since this was this is 23.5 meter image, list 3 image, so around about you can say 24 meter approximately size per pixel. So this is the output of that, which you can sober filter. You can still see the outline of different classes, right? Outline forming the river, the reservoir, the forest, etc. Right? And again, very high resolution image, UAV image, and all the boundaries. Even you can see the boundary of this car. Its bonnet, its shadow, its top is also segmented separately, right? Using the pixel-based classifier. Similarly, in the cars, their shadows are coming separately. Road markings, dividers, etc. coming separately using the boundary-based methods. Right? Different filters, Laplace, oval, Forte. Then watershed is also one of the boundary-based methods. Now, watershed, it uses the concept of watershed. So the concept of watershed is that it's a topographic surface which has valleys and mountains, right? So the image is assumed as a topographic surface with valleys and mountains. That means DN values, instead of assuming that they are DN values, it is assumed that it represents the altitudes. Right? Now, suppose in the valley, in the dip, there is a hole. Right? And suppose if we could lift this surface and put it inside in a lake. So wherever there is a hole, the water will start filling it and it will start flooding the surface. Now there will be more than one minima. So to avoid the water coming from two different minima, to meet, a dam will be built at that place. A dam will be built at that place, wherever there would be merging. So once it is segmented, the final output will be only the dam lines or the watershed lines. So this is again a boundary based method. So in this, there will be three kinds of pixels: the local minima from where the flooding will start, the catchment basins, right? That means the regions which are having which will belong to the same region. That means water flowing through this region will reach that common local minima. And there will be the boundaries, the watershed lines, which will avoid water from flooding from two minima. Right? So this is watershed segmentation. But the result of this watershed segmentation comes good in the X-ray images and all, but I have not seen very good result in the remote sensing satellite images. It has a problem of over segmentation. So very small segments are formed in the remote sensing data. So it requires a lot of region merging and the edge information to be incorporated in the segmentation. So I generally don't prefer to use watershed in the remote sensing data, which is having high peaks, but it works very good with the X-ray images and the medical image processing. Then the softwares which are used for object-based image analysis and image segmentation, I have tried to list here only very few for the Earth observation data. So the for Earth observation data, we use IIRS Imagine software, the IIRS Objective, right? NV feature analysis, the feature extraction module, Spring software. Perbath is a freeware. It was developed by one of the PhD student at ITC Netherlands, and after his PhD, he has made it as a freeware for people to use it. Then the software that I have been using quite a lot is the eCognition and the Definiance software, which is a very powerful software for object-based image analysis. Then simple segmentation algorithms you will find in large number of other softwares also, ImageJ or Q, etc., GRASS, OSIM, QGIS, etc., the image processing plugin. But mainly for the Earth observation data, we are seeing a very powerful software which I have been using is the eCognition software. Now coming to some case study examples which I have done, which I or my students have done at IIRS Dehradun. The first study that we did was two initial studies to check the accuracies of comparing the accuracy of object-based classifiers and simple pixel-based classifiers on different high-resolution data sets. Also, we wanted to determine what would be the scale parameter at each of the different resolution. Right? So we used a QuickBird, an IIRS image, list4 image, list3 image, right? And to segment, and we determined what would be the scale parameter for each of the satellite data in different scenarios of Indian study areas, and what were the accuracy of object-based classification that was achieved was reported here. Right? And you can see the classification results are so smooth. Another initial studies, was object-oriented classification for extracting urban features for high-resolution data. Again, for the part of Dehradun area, we used QuickBird image, IIRS image, as well as list4 image. Now, in the previous one was simple nearest neighbor classification and the scale parameter, what was the optimum scale parameter and the object-based classification. Here we tried to formulate different rules for the soft classifier, or different rules for different classes, like fuzzy-based rules were identified for different classes, right? And the accuracies were reported here. So in this study, we also did 3 levels of classification: level 1, level 2, and level 3 classification, going up to concrete roof, tin roof in the building, roads and bridges in the building, and so on. So the on different data sets, IIRS, the pan and multispectral fused image, QuickBird pan and multispectral fused image, and list4, the classification results were reported. The IIRS and QuickBird, we could do up to level 3 classification, but in the list4, we could do only up to level 2 classification. Right? And accuracies were reported. Then the accuracies of only extracting buildings, how much was the buildings which were extracted, their accuracies were also reported. Right? Then the another study which was done using object-based classification recognition software was tree line extraction. So the in this software, I don't need to do the entire land use classification, only the object of my interest, like for example tree lines, right? So I could formulate the rules for extracting only a single class, and the rules were formulated, segmented in classification, and the heights were estimated from the satellite image using the shadow concept. Right? So then from the ground-based tree lines, the tree heights were measured using the distance ristometers and the accuracies between the height measured from field and the height estimated from the satellite image, how much was the percentage of error, that was also reported here for different tree lines. Another study was to compare the road extraction using the recognition software and the IIRS Imagine objective software. So the using recognition software, various rules were formulated to extract only the roads from the data. Similar thing, the number of subsequent steps in the IIRS Imagine objective, and comparison of road extracted using the first method and the second method, their correctness, completeness, and quality was reported. Number of studies to establish the road and building extraction from satellite data were carried out to you can say to fix a methodology of road and building extraction using object-based classification method, and in different areas, different satellite data sets, and the accuracies and of completeness, correctness, and qualities were reported. Recent studies of building footprint extraction using the object-based classification, which were the parameters that were used, its comparison with the NV feature extraction algorithm. Buildings were extracted, manual buildings were digitized, and the comparison of the accuracies of the reference building as versus the classified using the multi-resolution algorithm and the rule-based algorithm was reported. Then another initial study was the agriculture field boundary extraction using high-resolution data. This study was done in different agriculture areas of Hisar, Pantnagar, and Saharanpur. Right? The field boundaries were extracted. There were errors in the field boundary extraction which were refined using the snake algorithm. Gaps were filled and the accuracies were another study was done using the worldview 0.5 meter San Francisco area, where in addition to the raw data, the digital elevation model was used. DSM image was used to extract the buildings and the different land use, and the comparison of buildings with the manually extracted and the roads with manually extracted roads were. Then simple object-based classification for the recent Cartosat data, Cartosat 2E data was attempted for part of Dehradun FRI area into different, very detailed land, you can say level 4 classification was done using the object-based classification on the Cartosat 2E data for Dehradun area by one of the PGP students. Right. Then this was the studies on the satellite data sets. Then similar studies were done on the UAV, which are very, very high resolution, centimeter level. The satellite images were 0.5 meters. Here it was 2 centimeter, 3 centimeter images. UAV images were used. But in the UAV images, the initial steps of photogrammetric processing have to be done. So ortho rectification was done in the AG software, and the segmentation and classification was done in the eCognition software. So this was the tree extraction and the field boundary extraction in a part of nearby Dehradun area, the image captured from a UAV, and the trees and the road boundaries were extracted using the combined flow of the georectification of small, you can say, UAV images, ortho-rectifying and making a mosaic of the images captured, and then segmenting and classifying them. Then they previously showed the UAV Hanover data where the small objects like trees and cars were there. So you can see here this study was done to extract the cars. Even their car bonnets could be separated, the shadows could be separated using the object-oriented classification techniques, road markings, and different trees, etc. were extracted. Then tree canopy and orchard geo-management study was also done by one of the MTech students at IIRS, and for a area Naharkoti near in the Dehradun district only. So number of images were captured by a UAV, and we developed the algorithms for shadow removal first of all for the UAV data set, then extracting the tree canopies using the slick that means simple linear iterative clustering, and then random forest classification approach, and then estimating the canopy parameters. Right? So this was the slick based classification and shadow region enhancement, right? So shadow region enhancement, you can see here. So the image was segmented, and this was presented in the conference in Indian Remote Sensing Conference, National Conference 2020, right? And the single canopy, double canopy, tree canopies were classified. The canopy parameters were extracted, and the results have been published in the Journal of Indian Society of Remote Sensing. So these were the various studies, very few studies which I've tried to compile here for the benefit of this webinar. So with this, I have finished with my session on the object-based image classification. We will take a break of 5 minutes and then we will continue with the question answer session, your discussion regarding your query.